The last lesson in Physics 20 is quarks, or quarks, as some people pronounce it. And this description is given to you in your notes, but I always like to do it anyway, just so you can see it as it occurs. Here is a neutron. A neutron is neutral. You would expect, so physicists expected that if I took, let's say, a negative particle, an electron, and I fired that electron by the neutron, what would happen? Well, it's neutral, so nothing. It shouldn't be, it should just go straight by it. But that's not what happened. They found out that if you shot an electron by a neutron, sometimes it would do this. It would approach the neutron and then go and be deflected away, which is mind-boggling. That should not happen. So, okay, so let's take an electron down here and let's fire that one by the neutron and see what happens. And so they did that, and they would expect it to either go straight or maybe to go down to counteract that so that they balance each other out to become neutral. But in fact, electron down here went like this. And this really baffles physicists because all of a sudden a neutron is not neutral. It should not be attracting or deflecting the electron in that way. So everything that we know up to now is wrong, or is it? And in fact, it's not wrong. The neutron is neutral, but this brought up the concept of quarks, which is that the neutron can be broken down into smaller subatomic particles, obviously called quarks, and those particles are positive and negative. Now, a neutron happens to be made up of two downs and an up. Two down quarks and an up quark. And a down quark has a charge of -1/3, and an up quark has a charge of +2/3. And you can see right away, and this is why the electrons moved in those paths, because if here's the neutron, if this upper part of the neutron has an overall negative charge, right, because this is where the down ones are, this is -1/3, this is -1/3, then it's going to be electrostatically repelled. And then this part of the neutron, the lower part of the neutron, is positively charged, and so it's going to attract that electron. But you can see, because it has two downs and one up, you add those together, what do they equal? 0. So it is overall neutral, but a neutron, we can say, has two downs and an up quark. And at that time, there were 6 different quarks discovered. The only ones that we deal with in Physics 30 are up and down quarks. So the other ones are beauty, strange, charm, truth. I think those are the other ones. Anyway, they're bizarre names. Up and down is just a little more for the simple-minded of us, like me. Okay, so now, yeah, you can go back and you can read about this. That's just an explanation of how we discovered these charges. And here's the same thing for a proton. And you can see a proton is made up of 2 ups and a down. And if you have 2 ups and a down, if you add all those together, you're going to get +1. Because 2/3 and 2/3 is 4/3. 4/3 minus 1/3 is 3/3, and 3/3 is 1, which again makes sense as to why the proton has a charge of +1. Okay, so there it is. That's the discovery of quarks. And here they all are. You only need know the up and down and their symbols. And just going back to our previous lesson on antimatter, obviously, since there's an up quark and a down quark, there must be an anti-up quark and an anti-down quark, which would have the opposite charges. All right. This information was good because it actually enabled us to explain how protons and neutrons become the opposite. And how does a neutron become a proton and transmutates into so the element changes. So for example, if you have carbon 6, and one of the protons, let's say you have carbon 12, and one of the protons becomes a neutron, so all of a sudden there's less 5. Oh, I'm so embarrassed. I don't know what 5 is. I have no idea. Becomes a neutron, right? Then the quarks can explain that. So for a neutron, let's so we've done this already. A neutron is made up of, a neutron equals 2 downs and 1 up, because -1/3 plus -1/3 plus +2/3 equals 0. And a proton is an up, up, down, because ⅔ plus ⅔ equals 1. So that's the explanation of why protons and neutrons are made up of the quarks that we claim they're made up of. Oh, this is another one of my favorite memes. I love this one. This was from, I put this meme up, I think it's 2012. This is when everybody thought, there were a lot of cultures that thought the world was going to end on December 21st, 2012. And as you can see, here's the forecast. And here's the high temperature, 990 degrees, and all hellfire's breaking loose. This is the apocalypse. Super cool meme. I don't know why this is in this video anymore, though. Oh, and this is an app. You can get this app that has all these subatomic particles and some information about each one, gives the mass, and notice the mass is in mega electron volts, gives the charge, gives the spin. You'll talk about spin if you do any university physics. I cannot speak intelligently about spin, so I'm not going to try. Oh, by the way, the weak nuclear force, I just saw that. And that's something I realized we haven't really discussed. The weak nuclear force is what determines radioactivity, and it's responsible for these neutrons changing into protons and protons changing into neutrons. So that's the weak nuclear force. Strong nuclear force holds the nucleus together. The weak nuclear force allows protons to change to neutrons and vice versa. Okay, and then so there's other examples of, look at that, anti-neutron. And a proton. Proton looking mighty happy because he's very positive. Fermion, what's this? This is an electron neutrino. A neutrino. And this is an electron anti-neutrino. Yep, and then here's the quarks. Look like guitar picks. The up quark is, they don't really look like guitar picks, just in this picture they do. Yep, gives you the information on an up and a down quark. And then we have this is the last thing, I believe, is it? One of the last things in physics 30. Can we use quarks and leptons to explain beta and negative decay? Yes, we can. So here's what's happening in beta negative decay. Remember, in beta negative decay, a neutron turns into a proton, and we said that's because the neutron is made up of a proton and an electron, right? But we can explain that also in terms of which we got right here. Neutron, proton, and then an antineutrino. Well, what actually happens is one of the down quarks changes to an up quark. And that's how we explain beta decay, the weak nuclear force. Okay, yes, blah, 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 and blah, blah, blah. And there you go, says the overall change is 0. So nothing changed. The overall charge did not change in this. We started off with 0 over here. What do we have over here? We have 0, because this is +1 and this is -1. So nothing changed except for a down quark changed into an up quark. And finally, but then we have beta positive decay, same thing. So here's a beta, here's a proton turning into a neutron plus a positron plus a neutrino. And in that case, an up quark changes to a down quark. And again, everything balances out because on this side of the equation, we have +1, and on the right side of the equation, we have +1. Where do we go from here? And then it just says, as far as physics 30 is concerned, you're done. But that doesn't mean physics is finished. You've gone about as far as the 1960s and 70s. So we're still 50 years behind here. There's a lot more to be done, and then talks about string theory and the grand unified theory, and you'll talk about the standard model if you do university physics and blah, blah, blah. The most important thing to know about physics is the more we learn, the more we realize we don't know. It's just we haven't even scratched the surface of what you will know in a couple hundred years. And it's kind of a paradox. As you learn more, you learn that you don't know more. So we'll know a whole bunch more, but we'll probably feel that we know even less. The universe and physics are even bigger a couple hundred years from now, or even at the end of your life. Anyway, that's the end of the videos for this. Farewell. Peace be with you. Live long and prosper. And we'll see you out there. That's from Star Trek. Bye.